Welcome all after a long break. In today's video, we will be dealing turbulent flow in circular pipe and simulate in ANSYS Fluent. We start with basic understanding of turbulent flow and its modeling in CFD solver. Then we perform simulation for a given problem in Fluent and compare the result with experimental correlation. Turbulent flow occurs when Reynolds number is greater than 4,000 for circular pipe, where inertia forces are more dominant than viscous forces. Above 10,000 Reynolds number, the flow is considered as fully turbulent flow. Most flows encountered in engineering practice are turbulent, and thus it is important to understand how turbulence affects wall shear stress. Turbulent flow is a complex mechanism dominated by fluctuations, and despite tremendous amounts of work done in this area by researchers, turbulent flow still is not fully understood. Thus, there has been a lot of experiments has been performed, and empirical or semi-empirical correlations developed for various situations. Turbulent flow is characterized by disorderly and rapid fluctuations of swirling regions of fluid called eddies throughout the flow. These fluctuations provide an additional mechanism for momentum and energy transfer. Therefore, heat transfer in turbulent flow is high compared to laminar flow. Turbulent flows are always transient, but we can solve the in steady state condition by time averaging of the parameter using Reynolds decomposition, in which fluctuating component is time averaged to get the mean parameters. Thus, we get average velocity profile as shown on figure 5. Turbulent flow is very hard to model. Even small change in any quantity change the result. There are 3 approaches to solve turbulent flow. First is DNS direct numerical simulation, in which fully unsteady Navier-Stokes equation are solved. But this comes with very high computation resources and time. Thus, it is not feasible for common turbulent flow. Second is LES, large eddy simulation, where some turbulence is directly solved. This technique is less expensive than DNS, but its application very limited. Third is Rans-Reynolds average Navier-Stokes simulation, which solves time average Navier-Stokes equation. This approach is widely used in application. Unlike laminar flow, the expressions for the velocity profile in a turbulent flow are based on both analysis and measurements, and much flatter compared to laminar flow, and thus they are semi-empirical in nature with constants determined from experimental data. The simplest and the best known is the power law velocity profile. Hydrodynamic entry length is much shorter in turbulent flow as expected, and its dependence on the Reynolds number is weaker. It is 11D at Reynolds number of 10,000 and increases to 43 at Reynolds number of 10 raised to 5. In practice, it is generally agreed that the entrance effects are confined within a tube length of pen diameters. We will use the 2 correlation. One is widely acceptable, is 10 times the diameter of pipe, and other correlation, which is used in Fluent documentation. Here is the problem in which we consider flow in circular pipe, considering Reynolds number equal to 10,000. Following is the calculation required to find out the first layer thickness, growth rate, and bias factor. In turbulent flow, Y plus is important parameter to consider. It defines how small mesh size to be to accurately capture the gradient near the wall. Here we consider 2 turbulent model. One is realizable K epsilon with enhanced wall treatment, and other is SST K omega model. Both models widely used to solve turbulent flows. And here is the summary of calculated parameter, which we will compare with Fluent simulation. First, open Design Modeler and create the geometry as shown. And this problem will be solved using axis symmetric. Draw a rectangle of height equal to radius of 12.5 millimeter and length equal to the length of the pipe, which is 3 meters for this problem. create the surface from sketches, change surface to fluid and exit design modeler. Open mesh and generate default mesh. Apply edge sizing along the lengths as shown. While giving edge sizing, change behavior to hard. Apply edge sizing with bias factor on both inlet and outlet. Select the edge and verify the bias factor is right direction. If not, use reverse bias. Give number of divisions as shown on the calculation slide, which is 50 division. Add face meshing for structured mesh. After mesh has been generated, verify the first layer thickness. Select the first and adjacent node. The distance will then display at the bottom. To check the mesh count, go statistics under mesh. This will show nodes and elements counts. Give name selection as shown. Select edge, press Ctrl+N, and give a name as inlet. Similarly, at opposite end, give named selection as outlet. Select top edge and give a name selection as wall. And for the bottom edge, give named selection as axis. Select body and give named selection as fluid domain. Now we will open Fluent and set up the CFD solver. Click double precision and use 2 processors. If mesh count is high, use higher number of processors depending on CPU installed in the system. Use pressure-based solver under steady condition. Change 2D space as axis symmetric. For this problem, first, we will solve using K-epsilon realizable with enhanced wall treatment. Import material properties of water from Fluent database. In cell zone, condition change material name to water liquid. Give the boundary condition as shown. Give velocity boundary condition to inlet and specify the value for turbulence under the boundary condition. Set specification method to intensity and hydraulic diameter. Input the intensity as 5% and hydraulic diameter as the pipe diameter. Give same turbulence parameter in the outlet boundary condition. Create 2 report definition. One is for max velocity at outlet and other is average wall shear stress. This report definition will be used to judge the solution for convergence. If the value becomes constant after a certain iteration, we can say that the solution is converged. Change residual to 1 e raised to minus 6. Initialize the solution with hybrid initialization. Set the number of iterations to 5,000. Set the length scale method to user specified and change length scale to pipe diameter. Start the iteration. For the post-processing, we need 3 graphs. One is velocity profile at the outlet, wall shear stress along the length, and centerline velocity along the length. Create XY plot as shown and export using write command. This graph is then plotted on the next slides for the comparison, and then repeat the same procedure by changing the model to SST K omega model. Results are compared with correlation and error as shown. From the result, we can see SST K omega model has less error compared to K epsilon realizable. Each turbulent model gives similar velocity profile with different slopes at the wall, which is indicated by different shear stresses from the performed simulation following point have been observed. Realizable K epsilon with enhanced wall function is in good agreement to the Fluent correlation, considering constant shear stress value and good agreement for 10 times diameter. By considering the centerline velocity, becomes 99% to Umax, while K omega SST shows large entry length compared to K epsilon and exceed the value of the correlation, but it will be good agreement with large entry lengths. Correlation given by different authors. K omega should be studied in detail by considering mesh independent study and different turbulent intensity. K omega, despite giving higher entry length, their fully developed value are in good agreement with pressure drop and shear stress compared to correlation. Each turbulent model gives different maximum velocity at the center. Fluent Y plus maximum is 2.3 near inlet wall, but 0.5 across whole domain. You can use Mentor-Lechner wall treatment for better prediction of shear stress and pressure drop. Note for entry length, various other proven correlations are also available, but here are the bases. 10B only. There are numerous other correlations given different authors, which gives different value for same Reynolds number. We have not dived into complex mathematical representation of turbulent flow, and its derivation is beyond the scope of this video. Even though there are discrepancies between both the turbulence models, still it is widely used in industries. Following are the references for further reading. Did you think about this? Which turbulence model should be preferred for industrial problems? Constant of turbulence for a function of which physical parameters? Can we change default parameters? Thanks for watching the whole video. We'll meet in next video.